like they've seen this before, so it was pretty easy to them. What we're going to do with this, instead of doing a reflection or a rotation or any of that other stuff that we've done, I guess it was rotations that we did freehand, wasn't it? Instead of doing a rotation, we're actually going to do a dilation. So this is what I want to do, and Kenneth can yell at me right now, and Curtis can yell at me, because what I forget on all these?
Symbols.
I forgot my symbols. I don't know how in the world.
Man, you gotta remember this.
I know, I'm slipping. You can knock my grade down a few points.
Cameron?
Yep.
That's because you were Curtis.
So
Oh,
I-
it's been how many years for you? I think it's
What symbol is that? Shh. What symbol is that?
That's a ring.
A ray, right?
Put it out.
Now, what symbol is that? Segment, all right? What I want you to do first, you're going to take your ruler and you're going to draw ray CP. With the ray, what's Caleb know? If we name it CP, what do we know? You go from C through P. Do you just stop at P?
No, you keep going.
No, you keep going, so do that. Draw that ray, ray CP.
No, stop. It's not even Thanksgiving.
Then what are we going to do after that?
Do ray CR.
And?
Ray CQ.
So go ahead and do it. Draw all three. Draw it out. Probably have to draw it out a little ways. Don't just stop like half inch past it. Make them, so they go out pretty far out there. That's why I gave you so much paper.
I got it. So we're good. Oh, it's been there.
So if we got these rays, and if you're any kind of artist, and you look at that, Chloe, next person that's talking while I'm talking, it's going to be a detention. So if you're any kind of artist and you're looking at that, what's it look like is happening?
Splitting it.
Does it look like, if you look at it right, does it look like it's sort of making it three-dimensional? All right, looks sort of like a pyramid, like it's three-dimensional, right? So that's what we're doing. With dilations, that's what you're going to be doing. Sort of making it like it's three-dimensional. So maybe if you were looking from this angle right here, it looks like if I'm standing at point C, it's shooting out this direction. Now, the next thing we want to do, we want to measure segment CP. So the distance from C to P. Use the centimeter side of your ruler. Don't use the inches.
It's about
Too difficult.
5.5.
So centimeter.
Use the centimeter side.
It's about 5. 4, 2.
About 5?
Yeah, 5 centimeters.
Mine's
Write that down.
5, wait, we're not, okay. 34.
Is everybody saying about 5 on CP?
Dude, 34 from.
About 5?
Oh, I got you.
Put it on line, just there.
Where'd you get 34?
Where'd I get 34 from? That's mine.
I got you.
Mine's a lot bigger than yours, right?
Wait, we're still pressing it on line?
No, mine's bigger than yours.
Oh, okay.
So you measure yours and write down your number. I gotta measure mine and write down my number.
It just didn't make sense.
And Chloe knows she didn't just stop there. What'd she go on and do?
You cute.
Measure CR, segment CR, and measure CQ. So go ahead and measure all three of them. So those are the measurements I got. Your measurement's gonna be different, right?
Yeah.
Now, the last one, I think CR, it didn't come out all real nice, did it? Like the other two
3
did.
7/10.
So what is it?
3 7/10.
3 7/10?
Right.
3.5 is pretty close. Instead of 3.5 or 3.7, I would probably, or 3.9, even any of those, I'd probably make it an even number, because I know what we're gonna do with it here in a minute, might make it a little easier. So if yours was not even like 4, but even like, you said what, 3.7?
Yeah.
So say 3.6 or 3.8, one of those two. Does that make sense? So just change it just that little millimeter. Now, with dilations you have K equals 2. You always have a number like this. Anybody know what that number is? What it stands for? If you've dealt with dilations in the past, it's the scale factor.
Oh.
Alright? So that means how much bigger or how much smaller are we making the shape? Well, this time if our K, our scale factor is 2, what are we doing to the shape?
Making it bigger.
Making it bigger. And all you're gonna do to make it bigger, somebody just said this, you're gonna take these 3 numbers and times them by the scale factor. Alright? So on your paper, if you times the first one by 2, what do you end up with? And what you're saying when you're multiplying by that number by 2, if this number on your paper is 5 and you multiply it by 2, then we're saying that P prime is not going to be 5 units from C, but it's going to be 10 units from C. And when we drew in this ray, the whole purpose of drawing in that ray, because P prime has to fall somewhere on that ray. It has to be on that ray somewhere. So is P prime going to be like right here?
No.
No. Is it going to be like right here?
No.
It's going to be out here somewhere, right? And that's all you're going to do. So now you're going to measure out and figure out where P prime is going to be. How far is P prime going to be from C? 10. So you're going to measure from C and go out here 10. Now I'm not going to do 10. What's mine going to be? 60, 68. So I'm going to measure out 68, which is somewhere right about in here. And what am I going to label that point? P prime. Can you do the same thing on the other two? Yeah, double them. And then measure out and put your new points. Make sure you're labeling your points. Mine's going to be way out here because I didn't make my thing big enough. It's going to be Q prime. When we take this test next week, if you don't put P prime, Q prime, and the correct primes or the correct labeling, it's going to be marked wrong. Gotta have those primes in there. Once you have your 3 new locations for those points, what are you going to do with it? Connect the dots. Connect those 3 dots. Hey, that's what we said at the beginning, wasn't it?
It's a beauty. It's a beauty.
Now, what's true about that triangle and the blue triangle?
It's getting 2 dots bigger. They're not triangle.
All right, now when you say it's 2 times bigger, does that mean 2 of these triangles will fit inside this triangle?
No.
That's not what it means. It means if I told you this side right here was 4,
That side's gonna be 4 too. That side's gonna be 8.
this side's going to be 8. All right, so the sides get bigger. I just made up. You just double it. All right, but it doesn't mean the area gets 2 times bigger. The area will actually go up by more than that. Okay? What if our scale factor, instead of being 2, what if our scale factor was something like 1/3? You times it by 1/3. What's that going to do to the shape? Is it going to end up out here?
No.
No. Where's it going to go?
Lower.
It's going to go back this way, closer to the center point. That's one of the key ideas today. If you're getting smaller, If your scale factor is making it smaller, you should get closer to the center point. If your scale factor is making it bigger, you should get farther away from the center point. So if it was 1/3, and if we were going to do this on the test, because I'm not going to give you a ruler on the test, if we were going to do it on the test, I'd have you do it this way. Everybody watching so you can understand this. We draw these rays in here, and then I just look at this, and if we're doing 1/3, what I would do, sort of separate this into 3 parts. Because this should be 1/3, that should be another third, that should be another third, right? Well, how many of the thirds do we want?
1.
1. So where's our new P prime going to be?
Right there.
Right there. And then I would do the same thing from here to here. Just try to estimate about 3 parts to Q. Mine looks like it's probably a little off. But Q prime is going to end up somewhere around in there, right? R, we estimate this. Does that look like that splits up about 3 parts?
Yeah.
Put R prime right there. And then we connect them. Does that triangle look the same as the other triangles?
Yes.
Yeah, it just got smaller. Now it looks even more 3D, right? It looks like we're going out through it. If I had 2/3 instead of 1/3, instead of going to this point, I would go to that one. Instead of this one that I went to, I'd go to that one. Instead of this one, I'd go to that one because I want 2 out of the 3. Does that triangle look the same as the other ones? And could we continue on like that? Again, anything that's a fraction, where it's getting smaller, it's going to get closer to the center point, wherever the center point happens to be. Anything that's a whole number, it's going to make it bigger, and it's going to get out here farther away. So if I did it times, if our scale factor was 4, it'd be way out here somewhere real big. Now watch closely on this one. What if our center point was something like this point right there? And I wanted it to get smaller. Well, this time, instead of our center point being off of the shape, away from the shape, now it's part of the shape. So everything, if it's getting smaller, everything's going to draw to that. So our shape would end up looking something like that, where this point doesn't move at all. If it got bigger, that point still wouldn't move. It'd just come out here, something like that. All right, my drawings aren't very good, but you get the idea, right? If your point's on the shape, what if your point was inside the shape? If it got smaller, what's going to happen to it? It's going to come in around it. Something like that. If it got bigger, it's going to go out like that. All right, so different places that your center point could be. Flip over on the back side of your paper. On the back side, we're going to do sort of the same thing, except looking up here as soon as I get out of the way, what's different this time? Our scale factor is a negative. Anybody have any idea what that's going to do?
It's gotta be smaller.
Now, does it have to be smaller because it's negative? But it is going to be smaller because it's a fraction, so it's 1/2. So it's going to get smaller. It should be closer, since it's a fraction, should be closer to C than the original one was. But where it's really going to change, because it's a negative, and Chloe might want to wait, she's not using her listening ears because she's drawing things. She doesn't want to draw it because she's going to be mad here in a minute.
Can you tell us what's left?
Because
It's going from P to C, not C.
this time when we draw this,
P's going to be the second step.
where do we start at?
P.
We start at P and we go out through C. When you have a negative, what happens with a negative scale factor? It goes back through it this way. Curtis, you listening? You didn't understand that when I said I was talking, and if you're talking to somebody else, it's going to be a detention? So we're gonna go this route this time. You're gonna start at the shape and go out through C the opposite way. That's what the negative scale factor does to you. So instead of being over here, now we're the other direction. The only time you do this is when the scale factor is a negative. Now you're going to do basically the same thing that we did on the other one. You want to know how far is P from C? Well, we already measured that, right? How far was P from C? 5. Only this time, instead of multiplying it by 2, we're going to multiply it by what?
Negative.
Okay, and you really don't need the negative, you just need to multiply by a half. We took care of the negative by coming this direction. Alright, so what is half times 5?
2.5.
2.5. So when we measure this out here, how far is your P prime going to be out here on this ray right here? 2.5. Now mine was, what was mine? 34, I think. And this one was 40. This one was 25, so I don't have to remeasure. So go ahead, you should be able to do it on your paper. Mine is 34, I want to take that times half, well that's like 17. So I'm going to go out this direction, 17.
So you do what, how you find it?
Take whatever the measurement from C to P is,
And you divide by,
we just want half of it. So 1/2 times that number. And this is going to be P prime.
why can't you just divide it?
Well, you divide it by what?
I don't know, 2.
2. That works for this one, but that only works if the top number is a 1. This one's 25, 1/2 times 25 is 12.5, so we're going to end up somewhere right in there.
3 plus 2, 5.
That's
Wait,
R
that's-
prime. 40, half of that. Half times 40 is 20. So we're going to end up right in here. That's Q prime. If I get a triangle that looks something like that,
Oh, you gotta do it,
Like how you,
down.
like, to shrink from like,
to shrink,
how do you do
because what we're doing, mine measured, let's take this top one. Mine measured from here to here was 34. Our scale factor is saying we want half that. So we take 1/2 times 34. And what's half times 34? 17, right? So I measured out here 17. P prime is going to fall on this ray, and it's going to be half as far from C as the original P was. Does that make sense?
So you just,
So you just take your numbers times
okay, times.
whatever the scale factor is. Now again, when you're doing the negative, you don't have to put in that negative number, because the distance that it is from C can't be a negative. There's no such thing as a negative distance. So even if we're out to this direction, we're still a positive distance. And it erased all my stuff. Why did it do that? Huh? If I hit previous again. Next. No. Previous. 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 No. Previous.
Dang technology.
That's the first one. Next. Oh well. Does everybody sort of understand that?
You got read my buddy?
What do you gotta do?
Well, probably though.
Yeah. You don't know it's bad.
You always have it.
I'll be
on
here
PowerPoint.
next week.
Does that make sense? Kenneth, you can do all that?
Yeah.
All right. Again, where you're going to have trouble at is if like P is right there. All right. If that's our center point, and we want to reduce it towards that point or enlarge it from that point, then all that's going to happen, let's say we're going to enlarge it 3 times the size. Then that means we measure this, so it's about this long. That means we want to come out 3 of those. Well, there's 1 right there, 2, 3. So P prime is going to fall in this ray out there 3 times as far, or not P prime, what should that be? That should be Q prime, sorry. And then we do the same thing over here. R prime, I'm not going to have room, but we go 3 times that. So that's 1, 2, 3. We'd end up down here somewhere. Okay? If we were going to make it smaller, then just sort of separate this. Let's say we're going to go half the size, or our scale factor is 1/2. We're going to draw back to it, so I split this in half. That means we're going to put Q prime right there. Split this in half. R prime is going to end up right there. And our new shape looks something like that. Does that shape sort of look like the original triangle? Yeah, it just got smaller. All right, what you need to do, set that stuff, just set it off to the side, open up your books to page 204. Questions, problems off of 204 that you want to see worked.
We did 29.
So we're 29.
29.
Why are you laughing?
29 and 32.
What did you say?
Page the homework was on.
Ah, 204. Okay.
29. During a presentation, a marketing representative uses a projector so that in the auditorium, so that everyone in the auditorium can view the advertisement. Is this projection a congruency transformation? Is it a congruency transformation? When I go back and look at my computer, let's say this is our advertisement right here. Is this the same size on my computer as it is up here? So is it going to be a congruency transformation? No, it gets bigger or it gets smaller, right? One of the two. So we write no.
Unless they're the same screen.
Right, unless both screens were the same size, and then, so if this was our advertisement, and everybody in here could see it from where you're at, would I need to put it on the projector? No. So they said he needed to put it on the projector so everybody could see it, so it must have gotten bigger. So a congruency transformation is when you have something, you transform it to somewhere else, but it stays exactly the same. Explain your reasoning. How come it's not a congruency transformation?
It gets bigger.
Got bigger. Hopefully it got bigger, right? If you want them to see it, hopefully it didn't get smaller. Next question. 32. Tesselation. We won't talk a whole lot about tessellations, but might bring them up later on in the book. This is all a tessellation is. Usually I give a quiz over tessellations, and you have to turn it in. And it could be as easy as this. You want to make a tessellation if this is our plane.
What is that?
That's a tessellation. All a tessellation does is it takes shapes. I have a whole bunch of shapes there, right? And it covers the entire plane. No gaps, No overlapping. So you can't take one shape, so it can't look like this, Curtis. If I was gonna do another plane and I was gonna use circles,
Oh, I can see now, alright.
see how you have a gap right there?
Yeah.
Can't have that gap.
I understand.
Alright? So that's a tessellation. Now what they wanted is they wanted you to be a little more creative than me just drawing a bunch of shapes, crazy shapes on there. So they wanted you to do something like maybe using rectangles.
Well, that's not really.
Yeah.
Yeah, it's not, I'm not all that creative of a person, so we're gonna go with it.
That's dope.
Maybe something like that. Alright? That's a tessellation. We took that shape and just moved it around somehow to cover the entire thing. You probably remember a 5th grade teacher, or 6th grade teacher, or 4th grade teacher, something that had these little boxes and it had a bunch of shapes in it, a triangle and a square and a rectangle, and it had all kinds of stuff. And you had to try to put all those in there to cover up the whole thing. And they all fit in there, and they only fit in there one way, and you had to figure out how to get them all in there. And you probably, you put in your triangle, then you put in your rectangle, and then you put in your square, and then all of a sudden you get down to the very end, and that last piece, you'd have some stupid looking shape that nothing will fit in it, and you'd have to start all over again. Other questions? When we do tessellations later on in the year, it'll probably be something like a real life situation. If our floor here is a tessellation, what shape does our floor use to cover the whole thing?
Square.
Square. All right. Now some of you may have a mom that doesn't like just squares, so maybe she asks somebody to come in and put some fancy design on her floor.
I think hexagons would be cool.
All right. Maybe hexagons.
That'd be dope.
So if we tried to do hexagons, what we could figure out, that's not a hexagon, what we could figure out, we could look at this, and this is probably what we're going to end up doing later on in the year. Would hexagons tessellate over this floor and cover the whole thing without any gaps? I don't know. What we'd have to do to see.
They look like a honeycomb over here.
So would it work?
Yeah.
If it looked like a honeycomb? Yeah.
It looked
Makes you
dope.
wonder, bees are pretty intelligent because how much wasted space are in their honeycomb? None. There's none. Alright? So bees even know that hey, a hexagon will tessellate over an entire plane. Alright? Now will everything work that way? Would a pentagon work?
No.
No, a pentagon won't work. Alright, we'd have to stick something else in there to help. But a hexagon would. And the way we can figure that out is by figuring out what that angle is right there in that hexagon. What do we know about that right there? How many degrees?
It's like
360. 360. It's a whole circle, right? Well, how many angles make that 360 right there? 3. So we could just take that 360 and divide it by 3, and you get 120. Guess how much each one of those angles right there is? 120. Somewhere in my room here, I'm sure there's a hexagon on the wall over there. Guess what the measure of this angle right here is in this hexagon? 120. How about this one? 120. If it's a regular hexagon, it's always going to be 120. So with a pentagon has 5, right? So we take 360 divided by 5. Somebody help me out with the calculator. What's 360 divided by 5? I think we did this the other day. 72. So that means when we start to put these sides together on a pentagon, and they're all coming together right here at this point, this angle is going to be 72. This angle is going to be 72. This angle is going to be 72. How many 72s are we going to need to total up to the 360? 5. And what's that?
260.
So we'd have to have 5 of them together right there. Is that gonna work? No, it's not gonna work the way, because you can't fit 5 of them to come all together like that. Other questions? 21. On 21, watch, because I'm gonna do 19 first, to make sure you understand both these, because one of them's doing something one way, one of them's doing it backwards. Guarantee there's a problem like this on the test, so Brianna's watching very, very closely. On 21, we had this theorem last time, and it said if you have some shape over here, you reflect it over this line, then you reflect it over this line. If we know this angle, which this time they tell us this angle is supposed to be 84 degrees, my angle doesn't look like 84 degrees. Instead of reflecting it here, then reflecting it here, we had a theorem that said you could have just spun it or rotated it to there. But we need to know how much of a turn that's going to be, and our theorem said to take this number and do what to it? Times it by 2. So all you do is take that number and times it by 2. What's 2 times 84?
168.
So what we could say here is instead of flipping it over this line and flipping it back over this line, we could have just said we could rotate this how many degrees counterclockwise? 168. Now 21 does that backwards. Got to make sure you know this stuff. I know they used X and Y's. I'm not sure why they use X and Y's on this, and then in the rules they write, they use A's and B's. I'm going to use A's and B's, because that's the rules that we wrote down. Does anybody remember what rule when we were doing, what was this, a reflection, right? No, a reflection?
Yeah.
Which one was it? The rotation, right? So when we rotated, what rule told us AB goes to negative A, negative B? 180 degrees. Clockwise or counterclockwise? Counter? Both. They're the same, aren't they? You go 100, if I'm standing here and I go 180 degrees this way, if I'm standing here and I go 180 degrees this way, I end up in the same spot, right? So it doesn't matter whether it's clockwise or counterclockwise. So we know that we're rotating this 180 degrees. So we have our 2 lines here again. We know that we spun it 180 degrees. But this time, instead of knowing the 84 and finding the 168, this time we know the bigger number and we want to find this. Well, here we multiplied 84 times 2 to get that. What are you going to do to this number to get the smaller number? Instead of multiplying by 2, what do? Divide by 2. What's 180 divided by 2? 90 degrees. So what's the measure of that angle right there have to be?
90 degrees.
90 degrees. So those two would have to be perpendicular to each other, even though my picture doesn't look anything like it, right? Other questions? All right. What is a dilation? Need a volunteer, real quick. Austin's going to come up here. He's going to use my nice sort of flag that I had here. He's going to use C as the center point of that. So you're going to put C right in the middle of that. See that C right there? You're going to put it right in the middle of it. All right? Does everybody see that? Now he's going to grab it by the stick that sticks out of it. Right now it's exactly the same both places, right? Hold away from the board a little bit. Keep the C in the middle. What do you see behind it?
Reflection.
The reflection, the shadow, right? What's true about the shadow right now?
It's gonna be same size.
Is it the same size?
Yeah.
Pretty close. Move it out a little farther.
Get bigger.
It's getting bigger. Keep going.
Bigger. Oh geez. She's real big now.
It's getting real big, right? What is that? The shadow is a dilation. It's just like we were just drawing there. We could draw a ray from up there. That's like our center point. Come down through here. Hit right here. It's going to be a dilation. Go farther. Got even bigger, right? And it's just going to keep going and going and going as long as he keeps getting closer and closer to
Close up the thing.
that, to the projector.
Brother up a little.
All right? So that's a dilation. When a figure is translated, reflected, rotated, or dilated, is the image, remember the image is what you end up with, the pre-image is what you start with. Are the image and the pre-image always congruent to each other? No. When are they not congruent? When it's a dilation. When it's a dilation, they're not congruent. How about, are they always similar to each other? Yeah, even with a translation where it ends up, if I take this shape and I move it over to here, is it still similar to the original shape? Yeah, but it's also congruent to the original shape. All right, write down just this title. Start of your notes. When we're looking at these two shapes, what do you know about them? They're congruent, all right? They're exactly the same. How about when I'm looking at these two shapes? They're similar to each other, and that's part of what we're going to cover today, similar. Yeah. So what we're going to do, be able to identify and perform dilations. Remember dilations, you get bigger or smaller. Solve problems using scale factors. That's probably the hardest thing that we're going to do today, is dealing with scale factors. A lot of people don't ever seem to understand when you're looking at a scale factor. So again, just write down dilations. That's the title. On this, as you go to write this down, what I want you to write down on this, read this top part here, and I want you to write down the highlighted words on separate lines, and then just come up with a definition for yourself for each one from that info. Does that make sense? Then when you get down here, you're going to write this, and there's 3 things that have to occur when we're doing dilations, or 3 things that occur when we're doing dilations. And that's these 3, and you'll write them down. So I'll give you a minute. Go ahead. All right, a dilation. What's the key things for a dilation? That's probably the key right there. It's when you enlarge or reduce a figure. Center dilation, that's just the center point that you're pulling it towards or pushing it away from or whatever. A lot of times, when we're doing dilations, your center point will be 0, 0 if we're on a graph, and we'll talk about that more here in a minute. Scale factor. What could you write for scale factor? Yeah, maybe. I wouldn't make it that hard. What's scale factor telling you? How much bigger or smaller, right? These 3 things must be true. And then we talked about this on the other one. If P is your center point, number 1 says if P is your center point. So that means P is on the shape. Oops, on the shape. If we're getting bigger or smaller in relationship to that point, then P and P prime are going to be exactly the same spot. So it's going to grow or get smaller in relationship to that point. So on this one, you might just put P and C same. So P is the center point, or whatever the center point is. If it's on the shape, center is on the shape, or part of the shape. If P is not the center, then you got stuff like we were just doing on that paper. All right, where P is out here and the shape's over here. And the shape, if you're getting smaller new shape's gonna get closer to the center, right? If you're getting bigger, the new shape's gonna get farther away. We're gonna talk more about this equation right here on another slide. It'll be easier to write down then. When I'm looking at this, if I look at angle P right here, and Caleb's not gonna say I don't know this time. I tell him that angle P right there is 30 degrees. And then I ask him, what's the measure of angle P prime right here? What's he gonna say?
60.
He said, I don't know.
Oh, 30.
30. The angles don't change,
My bad.
all right? So if I told you this angle right here is 22 degrees, what's this angle right here have to be? 22. Now, if I told you this side right here was 5, does that mean this side's got to be 5? No, one's bigger than the other, and that's where we're going to need the scale factor. The angles don't change, but the sides get bigger or smaller. All right, go ahead and write these 4 things down real quick. Congruency transformation. Remember, with the congruency transformation, what do we know about the pre-image and the image? They're the same. Very good. They're the same. With similarity transformation, the pre-image and the image aren't the same anymore. Now they're similar. That right there is the symbol for similar. So congruent, we have the squiggly line and the equal sign. What do we get rid of for similar?
Squiggly sign.
What do we get rid of? The equals part, right? Don't get this confused with all the other stuff. We've done stuff that looks like this. What's that mean? About, approximately. This means congruent. We've actually used this symbol earlier this year. Does anybody remember what that symbol meant earlier this year? That one. Negates or not, right? Don't get the two confused. I'm not sure why some silly math person made the same symbol for 2 different ideas, but they did. Congruent figures, we talked about this last time. Congruent figures have the same shape and the same size.
Does that mean with this agreement,
Say again?
not
No, it says movement, so pre-image is, what did we just say, that symbol? No, and that's, probably shouldn't even wrote that up here. Because they use that same symbol for similar, all right? That's the symbol for similar. So what it sort of means, Austin, I think the reason they use it for similar, because they're not the same, but they are similar. Does that make any sense? So that's the symbol for similar. So the pre-image and the image are similar to each other. So same shape, same size if they're congruent figures. Same shape, maybe, but not necessarily the same size if they're similar figures. They could be different sizes. Now, when you look at these names, you got to be able to look at these names and do what I'm getting ready to show you. So Lexi's going to focus right here. Right, Lexi? And we're going to ask Caleb another question here. Angle A. I tell him angle A in this triangle is 25 degrees. What angle over here has to be 25 degrees, Caleb? K. All right? They have to match up that way when you're saying that they're similar or congruent. You have to match up the corners correctly. So segment AB has to match up to what segment in this other triangle? What segment would segment AB match up to? KJ. You got to make sure they match up correctly. Whether you're saying they're similar or whether they're congruent. Write scale factors at the top of this. Scale factors. We're looking at scale factors. If you're going to do an enlargement, then your K, your scale factor, has to be, what's this symbol mean? Which one is it? Greater than 1. Give me a number that's greater than 1. 2. Give me another one. 3. So on, so on. So your scale factor has to be something like that. How about this number? 5/4. Is that bigger than 1?
Yes.
Yeah. So that would be an enlargement. Any of those numbers would be an enlargement. How about this number? 105%. Is that bigger than 1?
Yeah.
Yeah. How about this number? 1.7. Is that bigger than 1?
Yes.
Yeah, all those would make an enlargement. If your K is bigger than 1, then you're enlarging the shape. If your K is between 0 and 1, then you're reducing the shape or making it smaller. Give me a number that's between 0 and 1.
0.5.
0.5. Give me another one.
0.4.
0.4. Give me another one.
0.7.
Give me something that's not a decimal. Chickens.
1/3.
1/3. Thank you. All those are reductions. If your scale factor is any of those, it's a reduction. What happens if your scale factor is exactly 1?
It's equal sign.
It's the exact same thing, right? So if I said take this shape to a scale factor of 1, what's it going to look like when we're done? The exact same thing. A dilation is a non-rigid motion. Remember, a rigid motion means that when I move this shape from here over to here, it looks exactly the same. A non-rigid motion means when I dilate this shape from here to something else, they don't look the same. One's bigger, one's smaller than the other. So rigid motion, they're exactly the same. Non-rigid, not the same. Handle all that, Curtis. If you have a negative scale factor, I think I'm going to jump around on my slideshow here. If you have a negative scale factor, what's going to happen to the shape? Maybe. Could get bigger, could get smaller. How do we know? Sort of the same idea as these, right? And that's the slide I'm going to jump to next, I think. So remind me to come back to this one. I'm going to end the show. Discard this and let's jump down through here and see if I can find it. Alright, if you have a negative scale factor, write this. This goes right along with the positive scale factor. Maybe I should have put this slide after that one. If you're on a graph and you have a negative scale factor, all you got to do is multiply. All you got to do is multiply. And we'll talk about that more here in a minute. With the negative scale factor, if you're not on the graph, or well, even if you're on the graph, these three things are going to happen. The shape will flip over the center. Remember how we did that one, right? It had to flip over. Chloe got all upset with me because she drew that ray wrong. I wasn't quick enough to tell her not to draw before she had to erase. If your K is between 0 and -1, somebody give me a number that's between 0 and -1.
1/3.
No.
Negative 1/3.
-1/3, thank you. If it's something like that, then it's going to get smaller and it's going to flip over the center point. What if your scale factor is less than -1? Give me a number that's less than -1. -5. If your scale factor was -5, the shape's gonna get bigger, but it's still gonna flip to the other side of the center point. Brian, any of that makes sense? Are you lying to me just so I'll quit talking to you? Are you lying to me for some other reason? So why are you lying to me then? Oh, okay.
Psychology. Why do you have to do that?
What do I have to do? Record it? I put them on Moodle.
Why?
You know that?
So,
So for absent.
so if you're absent, you can get on there and get all the
But
notes.
we're not absent, so.
Okay, but what if you are? Would you like to have the notes?
Oh, it is.
Yeah, so Hannah might want to get these notes.
I'm gonna go back and hear myself on it.
You'll be like a movie star.
I'll steal your thing and post it to YouTube. You like this star?
They're
Pretty
already on,
sure that's-
they're already on
that's
YouTube.
What do you say?
They're all on YouTube, all these videos are. So
Dope.
you could probably go back here, Curtis,
Heck, I'm gonna sue you.
and listen to it. And
I'm gonna sue you. You know, information. I can sue you for
Look,
that.
Actually, I believe
you see
you.
me all worried about it, tears rolling
Hey.
down my cheek, right?
You know, if you agreed to be recorded out there, recording your voice doesn't matter, right? You called him Q earlier, remember?
I said the letter Q.
You definitely called him Q.
You know, Chris, you're always looking at me.
It's on video. Maybe I can listen to it later. Dude, where's my table?
I guess it's open.
Oh, you probably did though. That's nasty. That's gross.
Ew.
I ain't about that.
He sounds like I go around. I'm on bad.
Did you know 11,000 people voted for
It
Harambe?
was actually 15,000. Thank you very much.
Who cares?
Harambe does.
All right, on this, write this down to find. Dang, going it. I keep forgetting.
You're mad at Mobile Beach trash.
That's not what I wanted.
Bro, you're freaking nuts. Nigga died.
Write this down. This is probably one of the most important things of the day, because to find a scale factor should be extremely easy. But I guarantee on the test, because I've been teaching for quite a few years, that this is the kind of problem that everybody's going to miss. So if you write this down and you can follow this little formula that I have right here, it should be easy. To find the scale factor, all you're going to do is take the image length. Now, before I go any farther, image length. Which one is the image?
It's the second one.
The second one. Divided by the actual length, or the, what else? The pre-image. So you could write pre-image right here if you wanted. I put actual instead of pre-image, just hoping more people would understand it that way. So image divided by pre-image. That's going to give you the scale factor. Now when I'm looking at these pins down here in this first example, how do I know which one of these two pins is the image and which one's the pre-image?
The image is on
The prime. When I have the prime, which one is that? The image or the pre-image?
Image.
That's the image. So this is the image. This is the
Pre-image.
pre-image. Now when I'm looking at that to find our K then, what number goes with the image? The 12. That goes on top. What goes with the pre-image?
8.
That goes on bottom. I reduce this, what will go into both 12 and 8?
4.
4 will go into 12,
3 over 2.
3 times, 2 times. What's our scale factor?
3 over 2.
3 over 2. Always make sure that your scale factor makes sense. 3 over 2 tells us what should have happened to the image, or should have happened to the pin. Should have got bigger. 3 over 2 is an improper fraction,
Yeah.
so it should have got bigger. Did it get bigger?
Yeah.
Yeah. And that makes it so it makes sense. You can realize if you had 2 over 3, if you turned them upside down, will that work? No. So you can tell that that's wrong. How about this one? How would I find K on this one? What goes on top? 30, everybody agree with that? 18? It's gotta be one of them, which one is it? Everybody agree with 18? How do you know?
Because the bigger one.
Oh, wait, no, there's,
The first one is the first one.
Which one's prime? That one there, right?
Yeah.
Where's the center at? Here? So if we do it this way, let's see. We do it 18 over 30, reduce that down. What will go into both 18 and 30?
6,
6 will go into 18,
3,
6 will go into 30.
5.
Is that shape getting bigger or smaller? Is that a
Smaller.
reduction or an enlargement? It's a reduction, right? Which one of these was the original paperclip?
The biggest one.
This one here was the original. So did we get smaller?
Yeah.
So is this the right scale factor?
Yep.
So you can check to make sure that you're doing it right, right? But that's your scale factor. Now some of you, Curtis has got these calculating and goes, oh man, I don't know what that is reduced. And so he divides it. 18 divided by 30. And that's going to give him 0.6. There's probably a button on Curtis's calculator that will do what to that decimal?
32 fraction.
Change it back to a fraction. It's probably right here. It says F to D. So if we put in 0.6, we put in 0.6 and we hit second, that FD button, what's it tell you, Curtis? 3/5. Is that what we said it should have been?
Yeah.
So you gotta be able to use your stuff. On this one, if I'm trying to find the scale factor here, guarantee I like these kind of problems for, so I'll probably put it on the test. So, nope, not if you're paying attention right now. So Evan says it's 4.
Negative.
Don't listen to Evan, because he's just throwing numbers out there, because he picks 2 numbers out of the problem and he says, oh, we're dividing, so I'm gonna divide those 2, and he gets 4. That's good, but that doesn't work. And now he's saying it's a negative 4. And we're gonna tell him, you're wrong twice, strike 2. What did we say on that last slide? What did the formula say? What over what? Image over pre-image. Which one of these 2 measurements is the image? That's the second one. Which one? Which one is the image?
oh, yes.
3? How can you tell it's the 3?
Prime.
It's got that prime with it. So 3 goes on top. What goes on bottom? Now what do we do with that? Divide it or reduce it down? What's it reduced to?
1/4.
1/4. Does that make sense? If we started at 12 and went to 3, did it get smaller? So does our scale factor make sense there? All right, write this down. All you're going to do when you are given a scale factor is multiply. That's all you have to do. Remember how we multiplied by 2? And you told me that your original segment was 5, so the new segment was going to be 10. This is what you have to do. I have this bad feeling. Lexi's not writing stuff down. When we do something that's on the graph, she's going to be lost. I hope not. Hope she's got it all memorized in that large brain that she has inside her head.
That a rose?
So if I gave you this shape and I told you it was a picture that was 5 by 7, and we wanted to make it bigger, so we wanted to have a scale factor of 3. We had a scale factor of 3. How wide would the picture be when we enlarged it?
6.
What do we do with these 2 numbers?
Oh, 15.
15.
And 35.
How long is it going to be? Be careful.
21.
21.
Uh-huh.
That's all you do. If you know the scale factor, you just multiply by the lengths.
29.
If you're on a graph, I won't say it again, shut up. If you're on a graph and you're given points, so maybe I had a point like 2, -1. All you're going to do is take that scale factor. If it's a scale factor of 3, we multiply this x by 3, we multiply that y by 3. What's our new x coordinate going to be? If our scale factor was 3, what's our new x going to be?
6.
What's our new y going to be? All you do is take k times this, k times that, and find the new points. So if you're on a graph, you just multiply that by all of them. Now you're probably not just going to have one point you're going to have to do that to. If you're on a graph and you have a triangle, how many points are you going to have to multiply that 3 by?
3.
3 of them, each corner. If it's a pentagon, then you're going to have to multiply it by all 5 corners, so on, so on, so on. Down here I did one. Our A started out at 6/8. The scale factor is 1/2. What's half of 6?
3.
So that's our new x coordinate. What's half of 8?
4.
So that's our new y coordinate. So to find those new points, you have to do this. You can't, if you're on a graph, you can't graph the first one and do like you did with the translation and say, oh, it's going to go over to here. You got to use the rule, graph the new points, then see where the new shape's at. That's for any dilation. So if I do this real quick, I'm just going to do this. If I'm looking at these points, you got to look at your numbers first, because when I put this on the test, can I just give you a full page of graph paper to do it on? No, it's going to be some little graph. So can we always just put the x and the y right in the middle? No. On this one, I picked out where I wanted it to go. I stuck the x down this way a little bit. So apparently that must mean I need a little more space up on top. I stuck the y over this way. Now I'm going to graph this. 2, 1, that's A. 4, 1, that's B. 4, -1, that's C. So that's our original triangle. Now when I do the scale factor of 2, what's going to happen to that? It's going to get bigger. And our center point, anytime we're on a graph, our center point is going to be 0, 0. So it should go so it's farther away from that center point. All I'm going to do is take this and our A prime, what's A prime going to be? I just take that 2 and I do what with the 2 and the 1? Multiply. What's 2 times 2?
4.
What's 2 times 1?
2.
That's that new point. What's B prime going to be?
8.
8. 2. What's C prime going to be? 8. -2. And now I graph those. 4, 2. 1, 2, 3, 4, 2. That's there. That's A prime. 8, 2. 1, 2, 3, 4, 5, 6, 7, 8, 2. That's B prime. 8, -2 is C prime. Does that triangle look the same as the original triangle? Yeah, it just got bigger. Did it get closer or farther away from this center point?
Further away.
It got farther away, didn't it? All right, got farther away. Now, Chloe said she was looking at the other one. How can she make sure that she's not looking at the wrong one? The prime. All right, so that's all you're going to do if you're on a graph. What you're going to do if you're not on the graph is what we did at the beginning of class. Draw those rays and figure out, okay, it's going out farther this way, so I need to be out twice as far, or 3 times as far. What's going to happen if we have a scale factor like 0.4? Just times everything by 0.4, and it might, your graph might be, you might have to go out like 2.6 or something. Can you sort of figure out about where 2.6 is at? Am I gonna take off points if you're this much too far away from 2.6? Probably not. We did this. Do this, not sure why I got another one on there. We did the scale factor if it's negative. When you're negative on a graph, watch, because I'm going to do this very, very quickly. When you're negative on the graph, F prime, instead of worrying about, oh, it's got to flip over and do all that stuff, all you're going to do is take the negative 1/2 times each one of these. What's negative 1/2 times negative 4? 2. Positive 2. What's a negative 1/2 times a negative 2? 1. What's G prime going to be?
1, 2.
1, 2. Close. 1 negative 2.
The next
What's
one's 1, 1.
H prime going to be?
1,
1, 1. You graph those new points and it's going to do all the flipping and everything for you. But that's what you got to do first, is find those new points. What's negative 2 going to do to the shape?
Make it a positive 2.
Make it bigger, and it's going to flip over the center point, probably 0, 0 if we're on a graph. So on this, you're making your own photo stickers. Your photo is 4 by 4. You want the stickers to be 1.1 inches by 1.1 inches. How could we find that scale factor?
Take the image,
Which is
the after one,
1.1 and divide it by
1.4.
divided by 4, and that should give you what the scale factor is going to be. This spider, you're looking through a magnifying glass at this spider, and the magnifying glass makes it 6 times bigger. How can we find the length of the spider looking through the magnifying glass? Take 6 times 1.5. Is multiply, because you're making it what? Bigger. What did I do to this shape to get it to that shape? What kind of scale factor would I have used? What would it be?
So it's going
Would it be a positive scale factor or a negative scale factor? It's going to be a reduction. That's true. Positive or negative? Negative, because what did it do to it? It like flipped it over. So it's going to be a negative, and it's going to be some kind of fraction, like 1/5 or 1/3 or whatever. All right, that's your assignments on 2 separate pages. Looks longer than it actually is because